The next concept is remainder and factor theorem. When we are doing remainder and factor theorem questions, we'll be using a lot of fx or px, which has the same meaning as when you let an equation equals to y. Just that, we can change all the values of x with other constants or variable. So let's say we have this polynomial. If we sub x equals to 2, we will present this as f bracket 2 instead of f bracket x, showing that your x is substituted by 2. Subsequently, all your x in your equation will be replaced by 2. Therefore, you end up with a number 27. And then if you're substituting, that's if you're substituting a constant. If you substitute a variable, like 1 over x, likewise, you'll be replacing all the x in your original equation with 1 over x. And then you present it as f bracket 1 over x. And then if you substitute x equals to y minus 1, then likewise, all your x will become y minus 1. So from the previous section, we can recall that our polynomial can be expressed as a product of the quotient and divisor plus our remainder. So let's say our divisor is x minus a. If we substitute x equals to a, you can recall that we are making 0, because here this portion will be equals to 0. This whole thing will be equals to 0, leaving us with the remainder. Therefore, that's how we prove the remainder theorem, whereby if a function is divided by x minus a, the remainder will be equals to f bracket a, which means when you sub a into your equation. So now let's go through the steps that we will need to use when we use the remainder theorem. So firstly, let's see this example where fx equals to 2x cubed plus 3x squared minus x plus 1 is divided by 2x plus 1. So step 1, let your divisor equals to 0. And then you shift your 1 over and divide by 2, you'll get x equals to negative half. Step 2, sub x equals to negative half into fx. So once again, you present this as f bracket negative half equals to, subsequently then you substitute all your x equals to negative half, end up with 2. Therefore, by remainder theorem, your remainder is 2. So this remainder theorem is very useful when you're trying to look for the remainder of something without finding the quotient and without going through the hassle of long division. So now let's move on to factor theorem. So what is a factor? A factor means a number will be exactly divisible by its factor, right? Like for example, if 4 is a factor of 20, it means 20 can be exactly divided by 4, which gives you 5. Therefore, when something is divided by its factor, there will be no remainder. So f bracket a, which means you substitute a into fx, will equate to 0 because there is no more remainder. It means remainder equals to 0. So now going to an example, find the value of k if this polynomial has a factor of x plus 2. So first step, you have to let your polynomial or your equation be equals to p bracket x. So step 2, you let your factor equate to 0 and then find x. So you shift the 2 over, you'll get x equals to minus 2. And then step 3, by factor theorem, you will sub your x equals to minus 2 into your px. So p bracket minus 2 and then equate it to 0. Because if you recall, there will be no remainder. So f, or in this case p bracket negative 2 equals to 0. So subsequently, you once again sub in x equals to negative 2 into your equation and equating it to 0. Then from there, you can find your k. equals to 4.5. So something to note when you are doing remainder of factor theorem questions is that when you are using either of the theorem, please state which one you are using. So in this case, you have to write by factor theorem, and in the previous example, you have to state by remainder theorem. Another thing is that remainder factor theorem can only be used when divided by a linear factor. So anything that is ax plus b. It can't be like a quadratic factor like x square, anything with x square or x cube or whatever in it. Now let's go through the examples. So this expression leaves a remainder of 2k when divided by x plus 2 and a remainder of k when divided by x plus 1, x minus 1. Find the value of h and k. So when you usually remainder factor theorems, they may combine the use of both in the same question. So you have to look out for keywords in the question to guide whether you should use remainder theorem or factor theorem. In this case, it should be very obvious because they specifically told you that it leaves a remainder of 2k when divided by x plus 2. So this is your divisor. And a remainder of k when divided by x minus 1. So this is your divisor, your second divisor. So once again, your very first step, always let your polynomial be equals to fx. You have to make it equals to fx first before you can sub in any x values. Second step, you have to state clearly by what theorem. So by remainder theorem, and then by remainder theorem, f bracket negative 2 equals to 2k. So where did this come about? Looking at your very first divisor, the one over here, x plus 2, you have to let it equals to 0 first. So x plus 2 equals to 0. Then you shift your 2 over, x equals to negative 2. So that's why you sub x equals to negative 2 into your fx. Then they tell you there will be a remainder of 2k, so you equate it to 2k. So from there on, then you can continue to sub all x in your original polynomial with minus 2. And then when you expand everything, you eventually end up with this equation. 4h minus 3 equals to 2k. Now you can repeat the process with your second divisor. So your second one, x minus 1, we can let it equals to 0. And then shifting your 1 over, you'll get x equals to 1. Now you can sub this x equals to 1 into your fx to get your second equation. So that's why here you have f bracket 1 equals to k, because you equate it to your remainder of k. Your polynomial equate it to k, expand out all of these on the left hand side, and then you will end up with your second equation, h equals to k plus 3. So now you have two unknowns and you also have two equations, your first equation and your second equation. So you have to do simultaneous equations. So you substitute equation 2 into equation 1. So basically substitute h as k plus 3 into equation 1. And then you expand. And then you eventually get k equals to negative 9 over 2. And then you sub this value of k back into equation 2. Then you eventually end up with h equals to negative 3 over 2. That's how you get both of your values. So moving on to the second example, find the value of p and of q for which x plus 1 and 2x minus 1 are factors of this polynomial. So now that they emphasize that they are factors, of course, it must come to mind that you're using the factor theorem. Once again, step 1, let fx equals to your polynomial. Step 2, specify which theorem you are using. So in this case, it is the factor theorem. Step 3, find your divisor or your factor, in this case, x plus 1, let it equals to 0. And then find your x. So you shift your 1 over, you will end up with x equals to -1. So now you sub x equals to -1 into your fx. That's why you will end up with f bracket -1. And then remember, you will equate it to 0, because when you divide something by its factor, there will be no remainder, so it equals to 0. So subsequently, you sub your -1 into your initial polynomial, and then equate it to 0, expand everything, you will end up with your first equation. 2q plus p equals to 3. And then repeat this process for your second factor. So once again, emphasize by factor theorem. Find your second factor stated in the question, 2x minus 1. Let it equals to 0. Then you will get x equals to half. So note that there is an error here. This is not -half, so please cancel this out. It's just x equals to half. So you sub x equals to half in your fx. So here will become f bracket half equals to 0. Then you sub x equals to half into your fx equals to 0. Expand everything, and you will come to your second equation. Here. Once again, you end up with 2 unknowns and 2 equations, so you use simultaneous equation. You can use it in the substitution method, or in this case, the elimination method works also. If you add equation 1 and equation 2 together, you realize that p cancels out. So you end up with 2q minus half q equals to 3. And then you end up with q equals to 2. Then you sub this back into any of the equations. So for example, equation 1, maybe it'll be easier. So you sub q equals to 2. So it will be 4 plus p equals to 3. Then manipulate it, and p equals to -1. Therefore, you have your values of p equals to -1 and q equals to 2. Okay, now part 2 of this question. Explain why x minus 3 is not a factor of the expression. So what does it mean to be a factor of the expression? It means that there will not be any remainder when you divide by x minus 3, right? But if the question is telling you that it is not a factor, you are trying to prove that there is indeed a remainder when you divide by x minus 3. So how can you prove that? Once again, let your x minus 3 equals to 0, and then you will end up with x equals to 3. Now that you have this, you can sub it in equation to your fx, and you will see that you end up with 380, which is not equals to 0, which means that there is indeed a remainder. So by remainder theorem, once again, you have to emphasize, by remainder theorem, fx when divided by, change this to divided by x minus 3, leaves a remainder of 380, as we found here. Hence, it is not a factor. Okay, now example 4.2c. The function is defined by this, where a and b are constants. Given that x squared minus 3x minus 4 is a factor of fx, find the value of a and of b. Now, if you notice, right, the question gave you a quadratic factor. If you recall previously mentioned, it was specified that remainder factor theorem can only be used when divided by a linear factor. However, this time they give you a quadratic factor. So what do you have to do first? you have to further factorize this quadratic factor. So you can either use your calculator to factorize x squared minus 3x minus 4, or you can also use this cross method to get your factors. Okay, so your factors will now be x minus 4 and x plus 1. So if fx is divisible by x squared minus 3x minus 4, it means that your fx will also be divisible by the factors of your quadratic factor, so x minus 4 and x plus 1. Therefore, we can apply factor theorem for both x equals to 4 and x equals to minus 1, which is attained when you let each of these factors equals to 0 and solve for x. So let's do x equals to 4 first. By applying factor theorem, you can substitute x equals to 4 into your fx, like here. And then once you expand everything, you'll end up with your first equation. And then repeat it with x equals to minus 1, so you let equate to 0. And then you will end up with your equation 2 after expanding everything. So please also remember to state that it is by factor theorem. And then solving the simultaneous equation, you will get a equals to 2 and b equals to negative 7. So for now, let's skip part 2. I'll come back to it after we go through the section of factorizing polynomials. Now moving on to example 4.2d first. Please take note of what is written here. This is when fx is not given. So you'll see in example 4.2d, there's a difference in this question compared to the past few questions, whereby your polynomial or your fx was not given in the question. It is just stated here as a cubic polynomial fx. So please take note that when fx is divided by a linear factor, which means your power of x is 1, your remainder is equals to k, which is a constant number. However, when fx is divided by a quadratic factor, so the highest power of x is 2, like x squared, your remainder will be ax plus b. Okay, moving on. The cubic polynomial fx has a remainder of 5 when divided by x plus 1, and a remainder of 7 when divided by x minus 2. Find the remainder when fx is divided by x squared minus x minus 2. So you can recall that a function or your polynomial can also be expressed as a product of its quotient and its divisor plus its remainder. So with this formula and the context of the question given, we can form fx equals to x minus 2 and x plus 1. This is from the factors or the divisors given in the question, times quotient qx plus ax plus b. So this is the remainder. We are using ax plus b because, okay, linking back up here, we are dividing by a quadratic factor, this one. So you use this remainder, ax plus b. So we will end up with this whole chunk as our fx. Now we can just continue per usual using our remainder theorem and substituting f equals to minus 1 once again from letting this equals to 0, and then solving for x. Sub in into x that we had, equate it to negative 5 because it tells you in the question remainder of negative 5. And then we form our very first equation. And then by remainder theorem again, we'll repeat the same thing with our other factor. So let this equals to 0, then you get x equals to 2. And then you sub it in, get your second equation. Then you will solve for simultaneous equation, and then you get your values of a and b. And subbing these values back into the remainder ax plus b. Then you get 4x minus 1 as your remainder, and that is your answer.